So this video is a rare follow-up to last week's video where I tried to demonstrate that heat treatment doesn't affect the stiffness of a material, especially steel, or at least it won't cause any more or less bending given the same load. Now I was expecting some pushback on the topic given that it really isn't an intuitive thing that happens, but I think there were one or two areas where I could have been a bit better in how I demonstrated or described these properties of materials, and if I'd done so, it could have probably avoided some of the unnecessary, discussions that were seen in the comments. So the goal here is just to convey it a bit more clearly and hopefully avoid any of the confusion that I might have caused last week. So let's rewind to the beginning of last week's video and start from there. Also, if you're still in doubt by the end of this video, all of this information can be found in a basic engineering or materials textbook. So the whole premise around this video is centered around stiffness, hardness, and strength of steel. I mean, you can apply it to most metal alloys, but as I mentioned, steel is a bit of an outlier with metals because of how easily and readily it can be heat treated. Most notably quench hardening, which affects several properties including hardness, toughness, and strength. But not stiffness, that isn't affected. Yes, aluminium can be heat treated, but it's a much longer, more drawn out process, and because I don't do as much machining with aluminium these days, I haven't covered that topic yet on the channel. So let's start off with the basics. If I take an unhardened piece of steel wire and I put it in the vise, obviously it's going to be pretty easy for me to permanently deform it. I push on it and it doesn't come back to its original shape. But if I take a similar piece of tempered steel, I'm able to put the same amount of force or even more force without it permanently bending. And the same is true for the bigger piece of steel that I heat treated last week. The end that I didn't harden, I was able to bend, but the end that I did harden, I wasn't able to bend. Even putting my whole body weight behind it, I wasn't able to permanently bend it. Now I think colloquially, we'd all say that makes it stiffer. That end that was hardened was stiffer. It even feels a lot stiffer. But what it actually is it is stronger. It has a higher yield before it permanently deforms. And I think this is where the big confusion arises, because whilst it does feel stiffer, it actually isn't. Now the reason why I've made these videos is because it's a very common misconception, and I've had people tell me to harden parts simply to make them stiffer or more rigid. I made a boring bar cutter a few years ago, and I had some people tell me that I should have hardened the whole shank rather than just the cutting tip, because if I did the whole shank, it would make the whole setup a lot more rigid. It wouldn't cause it to flex as much. And that simply isn't true. A hardened boring bar isn't going to flex any more or less than an unhardened boring bar. Now, of course, the boring bars that I do use, they're hardened to about 40 to 45 Rockwell C in hardness, which is actually at the low end of my hardness testing files. But I think the reason why they do harden them is to give them added toughness in case of a crash, prevent them from snapping or permanently bending, and also to reduce wear from accidental rubbing if the hole is too small. And of course, I'm sure we all know that if you need to make a boring bar setup more rigid, you either reduce the stick out, you use a bigger tool, or you switch over to using a carbide boring bar. Tungsten carbide is about 3 times as stiff as steel, and it will make a boring bar that will flex less under the same load. I also want to point out that I'm not suggesting that people confuse hardness with stiffness. Several properties change in heat treatment, hardness is just one of them, and I believe people seem to confuse strength or an increase in strength with an increase in stiffness. Speaking of stiffness, let's use a proper engineering definition this time, because in the previous video I did simplify it down quite a lot, and I may have simplified it a little bit too much, which may have aided the confusion that some people had. So the definition that I'm going to use this time is directly from the American Society of Mechanical Engineers. And it reads as such: stiffness is the amount of force required to cause a certain amount of movement. And on the face of it so far, that is pretty straightforward and makes a lot of sense. But of course there is more. It is often referred to as the spring constant K. It is generally of constant magnitude and is expressed in units of newtons per millimeter. And unfortunately that is a bit more complicated. And finally, the elastic modulus represents the stiffness of a material. As you can see, that is a lot more thorough, but it is a lot more complicated. So let's try and work this through. And off the bat, I think it's clear that there are 2 parts here. We have our spring constant and our material stiffness. So first off, let's try and tackle the spring constant. So to really simplify it, the spring constant is how much force is required to move a spring a certain distance and still have it snap back to its original shape. There's a little bit more to it, but let's just stick with that for the minute. So let's just say, for example, I have a spring and it takes me 1 Newton of force to stretch it 1 millimeter. If we now abide by our spring constant, it's going to take 2 newtons to stretch it 2 millimeters, and then 3 for 3, and so on. The amount of force and the amount of stretch that we get is linear, or at least linear up until the point where the spring starts to permanently bend. Now let's just say we want to make a stiffer spring. We want there to be less movement for the same amount of force. And there's a few ways which you can do this. You can change the length of the spring, you can change the cross-sectional shape, you can change the cross-sectional area, or you can change the material. Now if you change any of these factors, the spring constant or the stiffness, by our definition, will change. If you're still watching, please bear with me, this will make sense in 1 minute, but can you see why I glossed over this in the previous video? But let's just continue. The spring constant can apply to pretty much anything, not just springs, so we can apply this to, say, a rod or a beam. So pretty much how stiff or how much we expect something to bend is based on length, cross-section, and material. And this is the reason why a ruler that's on its side is so much easier to bend than a ruler that is vertical. We haven't changed the material, we've just changed the cross-section. But obviously we aren't concerned about this part of stiffness, because in heat treatment we aren't interested in changing our dimension or shape, at least to the best of our ability. So if we aren't changing length or shape, the only other way that we can make something stiffer is to change the material, or at least the stiffness of said material. And I'm sure it's very obvious that each material has its own stiffness. If you have 2 rods of material that are the same diameter and length, obviously the one that's made of metal is going to be a lot harder to bend than the one that's made from plastic. The material itself is stiffer and it can't bend the same amount under the same force. But importantly, when we're talking about stiffness, it only applies if the material or the object springs back to its original shape. Now if you've looked up materials properties before, you may have seen this chart. What this is a stress-strain diagram, and it shows how a material behaves under tension. What happens to pretty much any material is that if we put a load on it, it'll stretch or strain by a certain amount. Now if we double the load, for most materials, the stretch will double in a linear fashion. In the real world, this is why the elongation of a spring is proportional to the applied load, or the deflection of a beam is proportional to the applied force. That is obviously up until a point though. If you push a spring too far, it won't spring back to its original shape, and if you bend a piece of mild steel too far, it'll deform and it won't go back to its original shape. Now the point where steel permanently deforms, we call that the yield point. For soft, low-carbon steel, it has a very low yield point. It doesn't take too much force to cause it to permanently bend. For springs, which are made of tempered steel, it has a very high yield point, and it takes a lot more force to get it to permanently bend. This is why we don't make springs from mild steel, because the first time that you load it up, it'll probably permanently bend, and that'll be the end of the spring. That's also why last week I was able to easily bend the unhardened piece of steel, but I was unable to do so with the tempered end. It takes a lot more force to get it to the point where it starts to permanently deform. Let's say for instance it might take 100 kilos to permanently bend the first piece, where it may take 150 kilos or more to permanently bend the second piece. And whilst it may feel like it's stiffer, it isn't. The steel here, despite it being considerably harder, is not stiffer. Now the way that we generally refer to the stiffness of a material is the modulus of elasticity, or Young's modulus. And what it is this straight linear line. And what it shows is that the force that you put in is going to be proportional to the amount of strain that you get out. And as you can see, softer materials have a very low angled slope because it takes less force to stretch it a certain amount compared to a more rigid metal. Under the same amount of force, we see less strain. And pretty much every metal and plastic is going to have a certain slope, or Young's modulus, although some aren't linear and they are a lot harder to quantify, although that's more of a material science thing and it's not worth worrying about in this video. Now let's talk about steel. The slope or the material stiffness is almost the same for every single alloy of steel, and it also doesn't change with heat treatment. Now the way that we measure it is in the unit pascals, or more commonly gigapascals. And you can look it up for yourself if you don't believe me, but pretty much every single alloy of steel, doesn't matter if it's heat treated or if it isn't, It'll have a modulus between 190 and 205, although some of them do occasionally go up to 210. Just looking at the SolidWorks material library, they're all between 210 and 190. And let's just say for argument's sake that the median value is 200. So we have 190 and 210 on each side, and that's about 5% each way, which is what I said in the previous video. You can judge for yourself if 5% is a lot, but I don't particularly think so, considering that tensile strength can vary almost 200% between the strongest and the weakest of alloys. It's also worth saying that adding carbon really doesn't do much to change the slope of the graph. What I have here is a graph of several different steels, with the only difference being carbon, and whilst it does get stronger, because this slope goes on for a longer period of time, the angle of the slope itself doesn't change, which means that the material itself doesn't get any stiffer. And it's worth stressing again, the only part of the diagram that we're really interested here in terms of stiffness is that straight line. That straight line is stiffness. And the reason for it is that any stretching or elongation or any force that's applied, once you remove the force, it will spring back to its original shape. It needs to be able to spring back to its original shape. And importantly, heat treatment will not change the slope of this graph. Now to show you again, I do have some very basic examples rigged up. If you're looking for some very precise lab-graded tests, unfortunately this won't be it, but it should help to drive the point home. Now last week I did a very simple bend test. Not the most perfect example, but I hope I got the point across. If you didn't see it, a long rod was put in the vise and a 9 kilo weight was placed at the end. And over a distance of about 45 centimeters, the end sagged about 10 millimeters, which means that it takes about 900 grams to flex it 1 millimeter. And within the elastic range, you would expect that to stay the same. I then took it to the furnace and then heat treated it to the low 50s Rockwell C hardness, and once the weight was put back on, the sag over 45 centimeters was 10 millimeters. It was exactly the same as it was before. Unfortunately, with it being heat treatment, part warped about 2 millimeters over the span of 45 centimeters. Not perfect because it will change the shape of the part that we're testing, and that does change the spring constant ever so slightly. But I don't think it was enough to really throw off the results. What's really important here is the displacement under the same force, and the displacement was pretty much exactly the same. There's a really good video on how to calculate the spring constant, and one of the most important data values is the displacement. I think it is true that it could have been a bit more precise, but I think the overarching point is that the stiffness wasn't affected because the Young's modulus of the steel wasn't affected. And over the course of the week, I have done 2 more examples. I can't claim that they're more precise, but they should help to get the point across. The first example is a spring, and to the end I'll attach a set of vice grips. Now the length of the spring beforehand was roughly 38 millimeters. And the length afterwards is 78. So the total displacement is 40 mil. Now the spring is made from tempered steel, so let's go ahead and normalize it. I'll heat it up with a blowtorch, which should soften it. Effectively, we're doing the exact opposite to what we did last week. Unfortunately, with it being hardened steel and with it being a coiled up spring, we are going to see some relaxing of stresses, and it won't be 100% the same length as it was beforehand. And after letting it cool, it's now grown ever so slightly to about 40 millimeters. However, once I put the vice grips on, it drops to 80 mil. The displacement is the same, 40 millimeters. A soft, unhardened steel spring is no more less or more stiff than a proper hardened spring. And that's because the material stiffness doesn't change. What has changed though is how much force that it takes to permanently deform it. Of course, it doesn't take that much more force to permanently flex it. Compared to beforehand, where it takes a lot more force to permanently bend it. And that is why springs are hardened, so they can take high loads without permanently bending. It's not to make them any more or less springy. And the same is true for metal rods, beams, or sheets. The other test that I did with some hacksaw blades. They're hardened, high carbon steel. However, I took one of them, removed the paint, and then used a burner to anneal it and make it soft. I then put some weights at the end, and as you can see, they pretty much flex down to the exact same spot. And just to show you that we're not cheating, that high carbon steel blade snaps very easily when I try to bend it, but with the annealed piece, it simply bends because it's not brittle. And I think the real question is, why is this the case? Now this is really getting more into materials science, which I did not study at university, but as I understand it, when we stretch or when we compress a material, we're stretching or compressing the atomic bonds between atoms. And different atoms have a different amount of force with which they bond to each other. That force is obviously less in a material such as aluminium than something that is stiffer, such as iron. Now in the heat treating of steel, we are able to rearrange the overall structure of the steel, which we call the grain structure. But that is a very different thing to changing the strength between the iron atoms. And that is what needs to be changed to change the stiffness of the steel. When we add other elements, the strength between those bonds are going to be different, and that's why we see a change in modulus when we have other elements alloyed in. But because most of it remains iron atoms and only a small percentage of other stuff is usually alloyed in, is why we see the Young's modulus remain between 190 and 210. So just to finish up, let me answer some questions directly about some of the points in the previous video. You'll have to deal with this because I didn't have any good B-roll to put on top of this. And the first one I want to answer is it fair to categorize steel so broadly as this? And in general, I do think it is fair to say that most steels have pretty much exactly the same strength. If you take a list of maybe the 10 most common grades of steel and you just look at the Young's modulus, or modulus of elasticity, you'll see that they all seem to fall between 190 and 210. I'm sure if you got every single alloy out there, you might see one that dips a little bit below 190 or one that's just a little bit higher than 210. But for pretty much every alloy that I know of and alloy that's in the SolidWorks and CATIA library, they all fall between 210 and 190. Now, is it true that somewhere there is a certain alloy that is designed to be at the higher end of that scale? 210, maybe a little bit higher than that? That could be true. I don't know of any alloy like that, but it could be true. But in terms of all the steels that I'm aware of, that being alloy and tool steels, they're mainly geared towards, high toughness, high tensile strength, hot working, cold working. Stiffness is not one of the properties that I'm aware that it specifically targets. If you know of one, that's really cool. I'd like to know of it and how stiff it actually is. But outside of that, I think it's fair to say that all steels are going to be, the same stiffness, plus or minus 5%. And this one here is probably true. 1045 is probably at the lowest end of hardenability as it could be. So you need to cool it down within about 1 second to form that hard martensite. And as a result, the inner core is probably left unhardened. With that said though, we're cooling it down in water and it's a pretty thin piece of rod, so I'd expect, the amount of hardness or the depth of that hardness to still be pretty substantial. Here's another one. Is it worth distinguishing between tensile strength and yield strength? In my opinion, for a basic video like this, I don't think it is all that necessary. Mostly because what we're really concerned about is yield strength. What is the point at which it stops bending, or at least, elastically bending and being able to spring back, and going to the point where it permanently starts to deform. At that point, that is the yield strength, and at that point, stiffness doesn't matter anymore. This comment here is saying that my definition could have been a little bit better in last week's video, and looking back on it, I do agree. I did oversimplify it just to make the video a bit easier to understand, and I think I may have oversimplified it a little bit. What I probably should have said was, how much force it takes to bend a certain material within its elastic limit. I think that little bit tacked on at the end would have made everything a bit more easier to understand. The next question is saying that I probably should have put up a graph of the different Young's moduluses of other materials, and to that, that's probably true. What I have here is a graph of different materials and their Young's moduluses, and obviously they will have a bit of a range because some materials are alloyed a bit more than others. I think the rule of thumb is to say that aluminium is about 1/3 the stiffness of steel, and going by this graph, it is roughly correct. The next question that's being asked is, what would be the performance difference between 3 boring bars? one made of tungsten carbide, one 13% cobalt tool steel, and one being made out of your regular mild steel. Now obviously tungsten carbide is a completely different material, and it's about 3 times the strength. The material itself is about 3 times the strength of, any steel. So we can obviously say that a tungsten carbide boring bar is going to be a lot stiffer. But the difference between the 13% cobalt tool steel and the mild steel probably isn't going to be a lot. I'm not exactly sure of any alloy that is 13% tool steel. I'm sure there is one. But I know that M42 cobalt steel, M42 high-speed steel is 8% roughly. And I looked that up and the Young's modulus for that was 200. I looked up the Young's modulus for a regular mild steel, and the range that I got was anywhere between 200 and 210. So interestingly enough, either the M42 cobalt steel would either be the same stiffness or maybe a little bit worse than that of mild steel. And it's also worth saying I did do my own tests, so this question here is asking, is alloying a contradiction? And I wouldn't say it's a contradiction because, it's a well-known thing that happens, and it isn't a heat treatment, which is what the video was specifically trying to address. Heat treatment won't change the Young's modulus of a material, especially steel, whereas alloying absolutely can, because we're changing the bonds themselves between the atoms. But then again, at least with steel, the only change that we're going to see is generally 5%. Now the next bit here is a little bit out of my wheelhouse because I didn't do material science, but as far as I am aware, heat treatment shouldn't affect the structure. The point about graphite, coal, and buckyballs and diamonds, as I'm sure we all know, those are all made of the element carbon. But the big difference between those and what we see in heat treatment, the actual bonds between the carbon atoms is different. And given that they have different bonds, the Young's modulus, as well as pretty much every other physical property, is different. And we do see that with these materials. With heat treatment though, we don't end up with different allotropes. Obviously when we heat it up, we form austenite, which is a different allotrope of steel. It's a physical rearrangement and a different bond. But once it cools down, we're left with our original alpha ion, which we started off with, and that shouldn't have changed at all. At least the bonds between those atoms. Now, of course, in terms of the larger structure, we can rearrange it because we do create grains, but that is different to rearranging the bonds between the atoms. That's why the Young's modulus doesn't change. And it's worth saying that for the rig in the previous video, I didn't change the material. All I did was I heat treated it, I hardened it to low 50s Rockwell C hardness, and in doing so, we shouldn't see a change in the Young's modulus. Now, if I got 2 different alloys of steel, say one that had 190 gigapascals as its Young's modulus, and I had one alloy of steel that had 210, and we put them up against each other, we should be able to see a difference. If we measure it precisely enough, we should be able to see a difference. But in terms of just heat treating that one test specimen, we shouldn't see a difference because Young's modulus doesn't change. And with that, thank you for watching. See you next week. I'll be back with more B-roll next week. Don't worry.